So, he defines X is said to be a good boy. If X is 20 years old. So we take a boy. How do we say he is a good boy? If he is 20 years. So if we take a boy, how old are you? If he says 20, yes, you are good. If he says 18, you are not good. That's the definition. So if you write if and only if, you know in advance that he is good without checking that. Do you understand what I'm saying? Here, when you have if and only, if only, you ask the boy, hey, how old are you? Then you say, okay, you are a good boy. Thank you. Here we are deciding, this is the way to decide that they are, say, triangles are congruent if what?
Choose that, this one.
This one?
Yellow.
Now, we say two triangles are congruent if, for instance, sets PQR, ABC, PQR, two triangles ABC, PQR, PQR. So two triangles are congruent if the set consisting ABC is equal to PQR. Assume that's the definition of C. So if you say X is ABC triangle is congruent to PQR triangle, if and only if, then you know in advance that they are congruent or not without checking this. So any book in the world that I have seen, nobody uses if and only. This is the only book. But we can say, no, he is bigger than everybody. I know, so somehow I am not happy. And there are so many illogical places. Okay, certain things are important. We have to know set theory a little bit, not much. To be an analyst, no, not only analyst, in pure maths you have to have little rough idea about sets. But set theory is a very crazy thing. We should not go to deep things in set theory, then we cannot do analysis. You talk about things that which never happen. Here definition, he says informal. We define the set A to be any unordered collection of objects. That's very important. Unordered. Unordered. You write them in braces. Whether you write 1, 2, 3 or 2, 3, 1. Order is redundant. Unordered. Order is redundant. But in a sequence, order is very important. We define the set A to be any unordered collection of objects. Objects. Then we have a question, what are objects? If you are very serious about set theory, then you talk about, hey, what is an object? So you talk about this thing, you kill days and weeks. Anyway, so I underline the word object. For instance, 179 is a set, you don't have to, you have to put the ones, no? If X is an object, we say that X is an element of A. Oh, this is how we say. I guess you know me. This pen is not. This is also address. Yes. X belongs to A. This means X is an element of A. Instead of saying X is an element of A, you can say X belongs to say A. Or if X lies in the collection, otherwise we say that X, this is how we say, we just cross it. X doesn't belong to A. For example, these are important at the very beginning. I have written 1, 2, 3, 4. This 2 belongs to this set, but 5 does not belong to this set. These are very simple things, but finally they matter. Axiom. Sets are objects. So these are little too much for us, but doesn't matter. Since we are following the book, we have to go through. If A is a set, then A is also an object, he says. Any set is an object. In particular, given two sets A and B, it is meaningful to ask whether A is also an element of B. Any in a set is a unordered collection, very important, unordered collection of objects. So one can ask, is a set an object? It is. Remark here, he says, there is a special case of set theory called pure set theory. No, I didn't go through the example. A is a set, then A is also an object. In particular, given two sets A and B, it is meaningful to ask whether A is also an element of B. It can happen. Example, informal. The set, this set, this set he says 1, 1, 2, 2. This is a set. One element or one object is again set of sets. It's a set of 3 distinct elements, one of which happens to be a set of 2 elements. However, not all elements, objects are sets. For example, 1 is not a set, but 1 is an element of that set. Here is a remark. There is a special case of set theory called pure set theory, in which all objects are sets. For instance, the number 0 is identified. This is the most famous one. Number 0 is identified with empty set. One other thing is, this book, the way he writes the empty set is again wrong. Empty set, you should write this way. He is writing like this. No? It is incorrect. Empty set, you have this. This comes from a Scandinavian alphabet. This is from Greek alphabet. Greek. So that's why I think maybe some Indian guys wrote some book and put his name. However, they also know a lot. That's how you should write your empty set. There is a special case of set theory called pure set theory, in which all objects are sets. So you write 0 by empty set, for instance. 0. This is 0. 0 is identified with the empty set. Empty set, you can write empty set this way also. Nothing is inside. Empty set, that's another way of writing. These are important. The number 1 is identified with 0. Number 1. This is 0. This is 0. 1 is identified with this, identified with 0 or like this. You don't need to think about it at all because we are not going to do it. However, this is the very famous one. But then you have to be very serious about things in order to understand it. I have written a little bit in this book, by the way, at the end, just a bit, couple of statements. 2 types of theories are more or less equivalent. for the purpose of doing mathematics. For us, we don't need to know too much of set theory for an analysis. Set theories are case people. Analysis people are, down to earth problems. No? Analysis is used by engineers so much. They make bridges, buildings, this and that. That is analysis. Set theory people, they don't do anything. They talk about things real crazy. And so we shall take an agnostic question as to whether all objects are sets or not. I mean, to us, it's not a serious thing. For us, if X is an object and A is a set, then either X belongs to A is true or X belongs to A is false. If A is a set and X is an object, either X belongs to A or X doesn't belong to A. No? If A is not a set, this thing is undefined. That's also important. Undefined. If A is not a set, A is not a set, X belongs to A, if X is an object, A is not a set, it is undefined, so we cannot use that in maths. And because we use statements which are meaningful in proofs. For instance, the statement 1 belongs to, here in your notes, 1 belongs to 2 is neither true nor false. If one can write this now, 1 belongs to 2, because this is not a set, that is neither true nor false, because 2 is not a set. Then equality of sets is talking about, we just need to go through them because it's important to have heard once. It says equality of sets, two sets A and B are. Actually, we can, without this definition, how do we say two sets are equal? Suppose you have two sets A and elements in capital A must be equal to elements in capital B. No? That's the only definition, only thing. So he is saying two sets A and B are equal. We write A equals B, by the way. If and only if every element of A is an element of B and vice versa. So what he is saying is, if the two sets are equal, both sets A and B have to have the same elements. But that is not the thing you can use when you are doing maths, because you are not getting this sort of sense. No? I mean, if you are getting this O level exam, that's okay. But for us, this definition is important. If and only if every element of A is an element of B. So how do we prove A is equal to B? So you prove for any object, X belongs to A if and only if X belongs to B. That's how we prove that the two sets are equal. So how do we prove this one? First you prove X belongs to A implies X belongs to B, and then X belongs to B implies X belongs to A. So the actual meaning is two sets A and B are equal, provided both of them have the same elements, and definition wise that is it. But mathematically, how do we say X belongs to A if and only if X belongs to B? How do we prove it? X belongs to A implies X belongs to B, and X belongs to B implies X belongs to A. In other words, A equals B if and only if every element X of A belongs also to B. and every element y of B belongs also to A. Example here is this, for example 1, 2, 3, 4 and 4, 1, 3, 2. I told you the order is redundant. In many places order matters. So, I have told you now, if you are given a sequence A1, A2, A3, if you order this way, answer can be 1948. You can change the order, say A100 plus A10 plus A50 plus A1, so on, maybe 8491. So order matters, but in the set, order is redundant. It doesn't matter how it is written. And another thing is, one can write, let's continue. For example, 1, 2, 3, 4 and 4, 1, 3, 2 are the same set since they contain exactly the same elements. Since a set A is an unordered collection of objects, order is redundant. Notice that the set 1, 1, 2, this set, here, 1, 2, this set 1, 2, 3, 4. Then he is writing 1, 1, 2, 3, 4, 3. So here in this set we have written 1 ones, 2 ones, 3 ones, 4 ones. Here in this set you can see 1 appear twice, 3 also appears twice. But if somebody asks you what are the members of this set, 1, 2, 3, 4, regardless of how many times it is written. So they are saying, usually we don't write this way. It doesn't make any sense of writing the same thing. Because what this means is, this is a collection of objects. It has one. How many times? It's not a question about sets. How many times is not a relevant question. So we usually don't write it that way. Equal to 1, 2, 3, 4. The repetition of 1 and 3 is irrelevant as it does not further change the status of 1 and 3 being elements of the set. And by the number of times it is written does not change the membership of 1 or the rather 3 to the set. So we don't write the same thing twice or thrice or more than once. One can easily verify the notion of equality of sets is reflexive, symmetric and transitive. Now, can you remember reflexive? These are very important in group theory, ring theory, analysis, everywhere. Reflexive. What is the next thing? Symmetric and transitive. These are obvious. Reflexive means, if two sets, if A is equal to B, then B is equal to A. Obvious, no? This is reflexive. Oh, sorry. Maybe I didn't have enough breakfast. Reflexive means A is equal to A. Reflexive means A is equal to A. That goes without saying, no? It's not a thing to discuss here. No? Symmetric means if A is equal to B, then B is equal to A. Symmetric. Doesn't order is redundant in other words. Transitive means if A is equal to B and B is equal to C, then A is equal to C. So set equality is it satisfies reflexive, symmetric and transitive. These are very important in analysis also, these properties. Thus the is an element of relation this belongs, obeys the axiom of substitution he has this axiom of substitution. I didn't care too much. Because what he says is, say, suppose A is equal to B and A is equal to A dash, then A dash is equal to B. So, maybe in set theory these are big things, but I didn't care too much. This is in the first chapter. I
A
didn't
dash
know.
equals B.
Eh?
Then A dash equals B.
A dash equals to B. Right. Axiom also. So I didn't pay attention because I don't want to get into too much of set theory side. I am interested in going to analysis side. So I am kind of making a rush because we have spent 1 month. No analysis yet, only logic, no? So you have somehow a good idea about logic, no? So when we are doing this, let's see his illogical basis. Let's point out there. Obeys axiom of substitution. However, we cannot use the notion of the first or last element in a set. You cannot talk about first element or last element. Sometimes in Sri Lanka, sometimes people ask you, what is the first positive integer? What is it? First positive integer.
The smallest positive integer is 1.
No, I am asking the first positive integer. Nothing like that, no? Third person, there is something like that. You are correct. The smallest positive integer is 1. So first and last positive integers in this course, is it plus? No. Is it plus? We usually write 1, 2, 3 like this. Doesn't imply that we cannot write like this. No? So that is first element or last element of a set. It's not a well-defined thing. These are good to hear at least once, though they are not very important. For instance, the sets 1, 2, 3, 4, 4, 1, 3, 2 are the same, but have different first and last elements. So, since the order is redundant, one can see right away that it doesn't make any sense to talk about first element, second element, third element, etc. Doesn't make any sense. Now we turn to the issue of exactly which objects are sets. These are serious matters, I don't like them. Issue of exactly which objects are sets and which objects are not objects. We begin by postulating the existence of the empty set. As far as you are concerned, to you there is an empty set, no? A set consisting nothing. But in maths, somebody can ask you, how do you know that there is an empty set? So that's why I told you that theory is kind of too much for us. But we have to see them at least once. Once is enough. Once is enough. So, here axiom empty set. There exists a set empty, known as the empty set, which contains no element. That is, for every object x, we have x doesn't belong into A. So, it is an axiom that there exists an empty set. If somebody asks you, how do you know that there is an empty set? It is an axiom. It's not that actually intuitively there is an empty set, no problem, but in set theory, they are very serious, very picky about everything. You have reasons for everything. So it is an axiom that there exists a set phi, not phi, empty set, known as the empty set, which contains no element. So contains no element means for every object, x, we have x does not belong into empty set. For every object x doesn't belong into empty set. The empty set is also denoted by, as I told you, this way, O level mass, you write this way, empty set, there is nothing inside. By the way, these are, you cannot put, these are called braces, these are called parentheses, no, these are called square brackets. What else? Right. Anyway, for a set, you use braces. No. The empty set also denoted by this. The empty set is unique. There is only one empty set in maths. The empty set is unique. There is only one empty set. To the contrary, I don't know whether it is proved in the book, I thought of proving. To the contrary, assume that there are two empty sets. Assume that there are two empty sets. One is y1, other one is empty set 2. Two empty sets. I want to prove that both are equal. So, I mean, this is obvious for us, but in maths, you cannot take anything for granted without a proof. That is the thing. Assume that there are two empty sets. Now let x be an object. How do you prove two sets are equal?
The element should be, every element in the first stage should be in the second element as well as and vice versa.
So that's how he said. That's not the again good way. So actual, this is the correct way. A is equal to B. How do you prove? For each x, for each object x, object x belongs to A, if and only if x belongs to B. This is the correct one, because when you say every element of A, I mean, this is how he said it, no? Every element of A must be an element of B. So it is assuming that A is non-empty. When you want to say every element of A, how can you say, how do you know that A is non-empty? This means you are proving this is equivalent to x belongs to A. Implies, I don't like to use the symbol, and x belongs to B implies x belongs to A. So that language is, that's why I told you that maybe some other people wrote it, the book. You cannot say every element of A is an every element. That is proved, I mean, for us, but in maths, when you are proving, say, A equals B proof, you write, you don't say let x belongs to A. Then you don't prove, then we prove x belongs to B. Oh, then we prove. This is not how it is proved. You cannot write that x belongs to A. Because then you have to know A is non-empty. You shall suppose x belongs to A. Then prove x belongs to B. Prove. We are on the way to prove that there is only one empty set. So, to the contrary, assume that there are two empty sets, empty set 1 and empty set 2. Now let x be any object. It's in the notes. Then both elements x belongs to empty set 1 and x belongs to empty set 2 are false. Both are false. Hence the statement x belongs to empty set 1 if and only if x belongs to empty set 2 is true. Hence empty set 1 is equal to empty set 2. Do you understand what I am saying? Huda, do you understand? So I did not say X belongs to empty Z1. I cannot say, I mean, empty set doesn't contain anything. What I am saying is, if you take any object X, X belongs to empty set 1 as well as empty set 2, both are false. From our logic lessons, X if and only Y, X if and only Y, if we say X if and only Y, that means X and Y are equally true, or else X and Y are equally false. That's what it means. So anyway, hence empty set 1 is equal to empty set 2, right? Clear? If a set is not equal to the empty set, we call it non-empty. That is clear. The following statement is simple but worth stating nevertheless. This is lemma. Single choice. Let capital A be a non-empty set. Then there exists an object X such that X belongs to A. If it is non-empty, it is so for us it is intuitive, but here there is a proof. But I don't need to write on the board. You have it. Single choice, we are choosing one. This is important. You will learn it a little later. Let A be a non-empty set. Then there exists an object X such that X belongs to A. And you see, this one allows you to say, suppose I say A is non-empty, then you can write let X belongs to A as a result of this lemma. If A is non-empty, it's kind of silly because A is non-empty, then you know that something is there. But mathematically you cannot take anything for granted without a proof. Let capital A be a non-empty set, then there exists an object X such that X belongs to A. Proof. We prove by contradiction. Suppose there does not exist an object X such that X belongs to A. Assume. Then for all objects X, we have X does not belong into A. Right? Also by the axiom of empty set, we have X does not belong to empty set. Right? Thus for all objects, X belongs to A, if and only if, I guess better to have X does not belong into A, if and only if does not belong into empty set, no? Let's change it. Thus for all objects, X does not belong into A, if and only if X does not belong into empty set. Let's change it then. Because both the statements are false, no matter which object. Do you understand the proof?
Yeah.
Because it's important, because in his case, definitely he is going to make a mathematician, so it's very good to be very serious at the very beginning. You cannot postpone to be, I will be serious tomorrow onwards. Nothing like that in maths. Today itself, you have to be serious. So you take any objects, since any object X, since according to our assumption, our supposition, X does not belong into A, again by the axiom of the empty set, X does not belong into empty set. So for all objects, X does not belong into A, if and only if X does not belong into empty set. Therefore, by the definition of equality of sets, A is equal to empty set, a contradiction. So it looks kind of silly, but to the contrary, it is important in maths. Remark, the above lemma asserts that, let's read this carefully, this paragraph. Above lemma asserts that given any non-empty set capital A, we are allowed to choose an element X of A, which demonstrates the non-emptiness. If A is non-empty, because of this what did he say? Single choice. Yes, single choice lemma. This proves that demonstrates the non-emptiness. Later, I am reading slow. It will be shown, given any finite number of non-empty sets, say A1 up to AN, it is possible to choose one element x1, x2 and so on up to xn from each set A1 up to AN. Now, we have proved that capital A is non-empty. We have shown that we can choose one x from A. Here this one is saying, if you have, say, A1 up to AN, some finite number of sets, then you can choose x1 from A1, x2 from A2, xn from AN. You can choose. Here he is saying, I didn't go to prove this thing. He says, given any. Later it will be shown. Since it is going to be shown in the book, I want to see the proof in the book. I did not try to prove it. If you have a non-empty set, single choice, we have proved you can choose one x from A. Here, later it will be shown, if A1, A2 up to A in a non-empty set, you can choose x1 from A1, you can choose x2 from A2, you can choose xn from AN. You must be listening carefully. This is known as finite choice. However, in order to choose elements from an infinite number of sets, suppose you have infinite number of sets, then you cannot say, hey, choose one from each number of sets. We need an additional axiom, the axiom of choice. Axiom of choice. This is really, really important. This funny little thing has changed the world of mathematics. You will learn it later. There is one book, not one book, one story. I mean, roughly what this says is, axiom of choice, if you have an infinite collection of non-empty sets, you can choose one from each set. That's what it says. In other words, if you have infinite collection of mango bags, you can choose one mango from each bag. Nobody can prove it. Nobody can prove it. So, we do it by axiom of choice. Modern analysis exists because of this. Modern analysis is here because of axiom of choice. You will see it later. We will discuss this. It is amazing. I have written one story here. I always use mango bags. I don't know why I go for mango bags somehow. This book. Maybe you can actually take a photocopy. Digamani. Yeah, Digamani. But now it is not that important. We have proved single choice. We are told it will be shown that finite choice, but infinite choice nobody can prove. As a result, we make it an axiom. And the funny thing is, because of this axiom only, modern analysis, what you call measure theory, analysis, exists because of this. If somebody asks you axiom of choice, I told you it already. If you have an infinite collection of non-empty mango bags, one can take one mango from each bag. If you tell to a man in the street, why do you make it an axiom? You take one and you come Ishwar. Can you see? So maths is something amazing, but so amazing. Axiom. Right? So this is axiom of choice. Single choice we have already proved. Finite choice we are going to prove. And infinite nobody can prove. As a result, we will make it an axiom called axiom of choice. As I told you, modern analysis exists because of that. It is so amazing that even to you may wonder why on earth, because this thing make modern analysis. Can you imagine? No, I cannot. Even today. Axiom, singleton sets and pair sets. If A is an object, then there exists a set. If A is an object, A is an object, then there is a set like this. This is an axiom. If A is an object, there is a set consisting A only. Consisting A only, whose only element is A. That is for every object Y. We have Y belongs to A. You don't want me to write on the board, no, because it is there. That is for every object Y. We have Y belongs to the set A if and only Y is equal to A. We refer to this set as a singleton set. Singleton. Singleton. I call it singleton A actually. Well, if you hear singleton, that means a set consisting only one element. If we refer to this A as a singleton set whose element is A, only element. Furthermore, if A and B are objects, then there exists a set. I mean, sometimes you may wonder why on earth we are learning this, we came here to learn analysis, these obvious things. But that's the way, If A and B are objects, then there exists a set A comma B, set consisting A comma B, whose only elements are A and B. That is for every object Y, we have Y belongs to A, B if and only if Y equals A or Y equals B. We refer to this set as the pair set formed by A and B. This is called singleton A. This is called pair set. Pair. So it is an axiom. If A is an object, there is a set which consists only that object, called singleton that object. If A and B are two objects, it is an axiom, there is a set which contains only A and B, that is called pair set A comma B. Remarks, just as there is only one empty set, there is only one singleton set for each object A. If you take an A, singleton A, again is unique. You try to write a proof. It's good for you to get into the habit of proving little things. Similarly,
in the pair set, it says for every object of Y, we have Y equals A comma B if and only if Y equals A or Y equals B, no?
yeah.
So is that or an inclusive or an exclusive or?
This is our maths O. Right? Because in this case, Y equals A and Y equals B, I mean, A and B are here. To understand this, we need to take A and B to be different elements. So, I mean, in here, inclusive, exclusive does not come. And the main thing is you need to remember is math O. That's the easiest way to understand. Easiest way. Again discuss both. There is one pair set form by. I have written discuss both. See, try to see whether you can prove this is unique and this is also unique. You can prove it. Just argue. That's good. Very little things. Notice that A comma B is B comma A and A is A. That's trivial because number of times A written does not change the elements in the set. Because you should not get confused with that. When I say it is not like a tea set. Tea set you have this sauce, then you have cup, and tea set. How many teacups are there? I don't know. Something. Then we have that, when you say tea set, some 6 cups and 6 sauces, something like that. So when it takes a set, it is very different meaning. Collection of objects. When you say a collection of objects, it's not like that. Here, if it is teacups, number of teacups is, and one teacup different, no? It's definitely different because in the set, say, suppose I write teacup, for instance. So what I know is that teacup is in this set. Then you cannot ask how many teacups are there in the set. Then you are thinking of that set. Can you see? In this, when I write here, teacup belongs to this set. So if somebody asks me how many teacups are there in the set, I cannot say. All I know is that it is there. So how many times tea set, when we say tea set in English, and here singleton tea set, very different meaning. So don't get confused. At the very beginning, these can be questions, but sooner or later you will get rid of them. Example, since empty set is a set, and hence an object, so is singleton set empty. This is empty set. This is singleton empty set. This set contains an element, that is empty set. That is the set whose only element is empty set. And these two are not the same. This is empty, this set is not empty. This set has an element that is empty set. Here this does not have anything. The set whose only element is empty set is a set and not the same as empty set. So I have written here they are not equal. Little things but important to know. Similarly, the singleton set, this one is also different. Now you get this one, this one, this one. Oh. That's another set. This set contains singleton empty set. Singleton. They are different. For us in analysis, these are not that important, but we have to know. Similarly, the singleton set, empty set, and the pair, they are also different. This is a pair set. It contains empty set as well as singleton empty set. So you need to be able to prove that they are different. Axiom, pairwise union, he is talking. Now it is bit important for us, coming to analysis type little thing. Pairwise union, given any two sets A, comma B, there exists a set A union B. In O level we just talk about A union B, but here some maths people are like that. How do you know that there is a union? So it is from this axiom, given any set two sets A, comma B, there exists a set A union B called A union B of A and B, whose elements consist of all the elements which belongs to A or B or both. So here I guess somehow he wrote both because you asked me inclusive, exclusive. He doesn't have to write which elements to A or B or both because we are doing maths. So, in other words, for any object X, X belongs to A union B, if and only if X belongs to A or X belongs to B. It can be belongs to both of them. Example, pair set 1, 2 union pair set 2, 3 is the set consisting 1, 2 and 3. Lemma. If A and B are objects, then A pair set AB is equal to the union of singleton set A, singleton A union singleton B. Lemma. If ABC are sets, then the union operation is commutative. We know them well, but proving is good for you because sooner or later you are going to prove terribly difficult things. But it will be fun. I like to do that kind of thing, but you know, I cannot pass these chapters. So you have to go through the chapters. It is like you go to lunch, you like dessert so much, but you can skip the lunch and eat the dessert, that kind of thing. That boy who laughs all the time is not coming. If we say that there is a lunch, he might come. Your friend, he is not coming. Why?
He has SIMA
exams. I don't know somebody who likes maths can do SIMA.
He's going engineering.
Eh?
He's going for engineering.
Engineering, yeah. To be successful in maths, you should do maths only. That's my idea. Because other subjects is an applied taste. No? Here, how do you know that there is an empty set? The physicians ask. Anyway, if ABC are sets, then the union operation is commutative. A union B is equal to B union A. And associative A union B, union C is equal to A union B union C. Also we have A union A is A, union phi union A is also A. And here I guess he has proved one, so I also sort of going through it to make sure that you get the point. Let us prove that the associative identity. We are going through this. We need to show that every element X of A union B union C is an element of A union B union C and vice versa. So somehow, I guess I have written what is in the book. Let me check. Starting the beginning where am I? We prove just the associate identity A union B, union C is A union B union C, and leave the remaining claims to exercise 3.1.3. definition 3.1.4, we need to show that every element X of A union B union C is an element. Somehow I don't like it that much, because when he says that every element, I wrote, because he is writing it this way, how do you know that there are elements in this thing? Because in my books, I don't write that way, and not only my books. Other people, I am sure this is, he hasn't checked. So what you said is, I mean, there are, I couldn't get exactly what you were saying. Now, this is Indian edition type thing, or are there other editions of this book? You don't know.
In the back cover, they said the Indian edition.
Indian edition.
In that online book. So I
Ah.
don't know about this.
Doesn't matter, these are little things, but little things matter to a beginning math student. Because at the very beginning you have to be pedantic and logical at the very beginning. That makes you a mathematician. So let's prove this one. Suppose we want to prove, we need to show x for each x belongs to A union B union C implies x belongs to A union B union C. This is, and vice versa, you have to do both. So let's do this one. So suppose, or assume x belongs to, because this book thing I don't like is sometimes it is so serious, sometimes not as serious as you, a beginning student. Assume x belongs to A union. He is taking which one? Let's take that's A union B. And you see, I did not say anything belongs to A union B union C. I said assume. Then x belongs to A union B O x belongs to A union B O x belongs to C. Now there are here two things. One way is x belongs to A union B, other way is x belongs to C. So as a result, let's take cases. That's the best way. Then you don't do any mistake, I guess. Suppose x belongs to C. If x belongs to C, then x belongs to B union C. So x belongs to A union B union C. Now in case 1 we are done. If x belongs to C, x belongs to A union B union C. Now case 2. Now suppose x belongs to A union B. Then x belongs to A, O x belongs to B. If x belongs to A, then x belongs to A union B union C. Right away I can say if X belongs to A, then X belongs to A union B union C. Why? If X belongs to B, then X belongs to B union C, and hence X belongs to A union B union C. Only thing is you need to be careful. Thus, in either case, X belongs to A union B union C. So I guess this is the correct way of writing, because sometimes he likes to, the author somehow tries to behave like, talks like a man in the street. Sometimes he is talking very rigorous, as a very rigorous mathematician. So when he says every element of these are man in the street statements. Similarly, I say it can be shown that
Other way. Yeah.
very similar, so we don't need to spend the time. Because of the above lemma, we don't need to use parentheses to denote multiple unions. We can write A union B union C without parentheses, because it doesn't matter how you take the, always you can take the union of only two sets, that's the problem. Because whether you have a PhD in math or not, you can add only two numbers at a time. That's why they are called binary operations. You cannot add more than two. Six. By this axiom, we can define triple sets, quadruple sets, and so forth. If A, B, C are three objects, we define A, B, C to be union A union singleton A union singleton B union singleton C. And if A, B, C, T are four objects, then we define, and so forth. It's nothing new. Definition. Subsets. Let capital A, B be sets. We say that A is a subset of B, denoted by A is a subset of B, if and only if every element of A is also an every element of B. Again, assuming that he cannot write this if A and B are empty. That's why I say this is true to a man in the street. A subset of B means every element of A is an element of B to a man in the street. But mathematically, you cannot say so. Anyway, that is for any object X belongs to A implies X belongs to B. That is true. We say that when you say for any object X belongs to A implies X belongs to B, and when you say every element of A is an element of B, they are two different statements. Every element of A is an element of B, that say that A is non-empty. When you say for any object X belongs to A implies X belongs to B, it does not say A and B are non-empty. So, because these are very important, I told you this infinite collection of non-empty, if you are given an infinite collection of non-empty mango bags, one mango can be taken from each mango bag, is an axiom that is the base of modern analysis that we are going to study later in the course. So it is very serious little things. That's why I say sometimes he is so serious, sometimes not at all, I don't know. We say that A is a proper subset of B denoted by A is subset of B is denoted this way. A is a proper subset of B is denoted. You cut here, like this. This is A is subset of B, and then one A is a proper subset of B. This means if A is subset of B and A not equal. Examples, let's see, I guess they are trivial. We have set consisting 1, 3, 5 is a subset of set consisting 1, 2, 3, 4, 5 because every element of 1, 3, 5 is also an element of 1, 2, 3, 4, 5. In fact, we also have 1, 3, 5 is a proper subset of 1, 2, 3, 4, 5. I mean, they are trivial since the two sets 1, 3, 5 and 1, 2, 3, 4, 5 are not equal. Given any set A is subset of A because every element of A is an element of A. Again, he writes like that. I wrote the same thing, but that's not the reason, however, because it's for each x belongs to A implies x belongs to A. An empty set is subset of A for any element. How do you prove that? It is proof is here, because for any object x belongs to empty set implies x belongs to A. Can you see he is playing around the bush? Sometimes he says when he is subset of B, he says every element of A is an element of B. But when he wants to prove why empty set is subset of A, he doesn't use that one. He is using x belongs to empty set implies x belongs to A. That statement is vacuously true. You see, did you understand what I'm saying? Uta?
Definition.
Oh, sometimes it's like some Sri Lankan people. Some university, I should not say the name of the university, lecturers, they together wrote a book for A-levels. So in that book, they have written principle of mathematical induction. Principle of mathematical induction, they wrote it. But I guess they copied the principle of mathematical induction from some book. You see, lecturers, they know what books know. However, when they are going to prove the problems, do the problems, principle of mathematical is in the jungle, they are doing the way they want. The same thing this person is doing. When he wants to talk about A is subset of B, he says every element of A is an every element of B. But when he wants to prove A, empty set is subset of A, then he goes to for every object x belongs to empty set implies x belongs to A is true. You understand what I'm saying, no? The notion of subset in set theory is similar to the notion of less than or equal to for numbers, as the following question demonstrates. For numbers, we talk about x less than or equal to y. They are similar in many ways. A is subset of B, x less than or equal to y. Proposition sets are partially ordered by set inclusion. Let me read it. Let capital A, B, C be sets. If A is subset of B and B is subset of C, then A is subset of C. If A is subset of B and B is subset of A is equal to B. Finally, if A is a proper subset of B and B is a proper subset of C, then A is a proper subset of C. So, these are for us intuitive, but we need to be able to prove because we are in geometry class and we are given definition. Nothing can be taken for granted without the proof. Here, I guess, proof. Let us show that A is subset of B and B is. Let me go to that. This is what I don't know which X is from somewhere. Sets are partially ordered, but let A, B, C be set. If A is subset of B and B is subset of C, then A is subset of C. We shall just prove the first claim, only this one. He says, suppose that A is subset of B and B is subset of C. This time he is good. He has written suppose. Because you don't know unless you say explicitly say, how do I know that A is subset of B and B is subset of C? So he is very good. Because statement says, can you see this can be written in two ways? See, suppose somebody, if A is subset of B and B is subset of C, then A is subset of C. This is one. Other time is oppose. A is subset of B and B is subset of C. Then B is subset of C. Oh, sorry. Roughly, both statements are the same. But when you are writing proofs, different, because here we are not told that A is subset of B and B is subset of C. When you are proving this one, proof begins from proof. You say, suppose, or assume, one of the words. Suppose, or assume, whichever you like. A is subset of B and B is subset of C. When you are proving that, you don't need to write that. Then you begin to write let X be an object. And then you say, suppose X belongs to A. Can you see the difference? Roughly the same, but not the same. It makes a difference in maths. අපි අර පැටිස් එක ගන්න ඕනේ.
කට් කරන්න